Okay, next idea is the Newton's law of gravitation. So you need to revise this. So for 2 point masses, let's say the point masses are capital M and simple m, and if they're separated by a distance r in space, right, any 2 point masses in the universe, they're attracted by two equal and opposite forces, right? Equal and opposite, equal to each other in magnitude and opposite in direction. And this force F is given by this formula Gmm over r squared, where G is a constant. G is the universal gravitational constant, universal gravitational constant, and it's a major constant in the universe. And the important thing about this is you can use this same formula. This is for point masses and point masses only, okay, for now. Then you have to understand you can extend this idea to scenarios like spheres in 3D, or disks. If the story is in a two-dimensional situation, disks, rings, right? As long as the two masses are like outside of each other, not inside. Like if you take a ring and put another mass here, or if you take a hollow sphere and put another solid sphere inside. No, these are not the cases that we're talking about. We're talking about scenarios where the two masses are like apart, right? And they should have kind of a radial symmetry. Radial symmetry in the sense like from the center, it should look the same in all directions. All directions of consideration. Like if it's a 3D scenario, a point can be inflated to being a sphere. Okay, if you inflate it in 3D. If you do the same thing in a 2D setup, it could look like a ring or a disc. This is two-dimensional. Sphere in three-dimensional, and sphere could be hollow or solid. It doesn't matter as long as it has that radial symmetry, radially same in all directions. So what's the important thing about this is, if I show you an example. So if you have a sphere like this, right, a solid sphere, solid uniform sphere. Uniform part is very important because the radial symmetry is to be there in terms of the mass distribution. Okay, it should be radially symmetric in terms of the mass distribution, not in terms of the shape. Because shape could be a sphere, but the mass distribution could be like not radially symmetric. So then this condition is not valid. So if say uniform solid sphere is there and another mass m, this one has a capital M mass, what I am telling you this is, now if this is the case, say this mass can be considered as if it's right there at the center. Okay, you can like kind of squeeze this mass into its center. Then consider this capital M mass and that capital M mass and the distance between them, and write the equation Gmm over r squared. So this is allowed as long as it's radially symmetric and the two masses are like outside of each other. So let me tell you what's not allowed at the same moment, because a lot of people misunderstand this by saying, we put the distance between the center of masses. No, not the distance between the two center of masses, because if you are given a case like this, where you have a uniform, say solid rod, okay, of mass m, and there you have the point mass simple m. Now say from here to here its distance is d, then one could take the center of mass of this thing to be here as a single capital M mass, and then F gmm over d squared. No, this is wrong, because it's not the distance between the center of masses. So in this equation, it's not for any two masses, it's for point masses. Point masses, that's a specific thing. So if you're not using it for point masses, then you have to be careful in your wording. So for spherically symmetric or radially symmetric mass distribution, radially symmetric mass distribution, that's one thing. The other thing is they're outside, right? Outside of each other, whatever this means. Okay, so I hope you understand that. So if this is there, then yeah, you can put the distance between the center of masses, but it's not a generality. So when the mass distribution is not radially symmetric, right, this is not radially symmetric, then this equation doesn't work. Actually, the correct version of this, one could say f is actually less than gmm over d squared. To be definite, it is actually less than gmm over d squared. And let's talk about that in a different video, okay, some other day. You can think about it and how to arrive at this answer. So that's it for this question.